3. Heap sort and efficiency analysis. So in this part, we will complete the heap sort. At the same time, we want to do the efficiency analysis. But with the preparation we have at this point, the analysis part is pretty easy. Yeah. All right. First, now, look at this. When we build heap data structure and we build a max heap data structure to store our data, the cost is relatively high, right? Yeah. We, spend many operations, mainly swap operation. So comparison and a swap operation. Yeah. So after we did big O of n, that cost operations, finally we get a max heap. Now we use this data structure, we can do the heap sorting easily. Yeah. So let's look at the procedure. Yeah. Key observation. Let's make this observation. Yeah. Suppose this is a max heap. Yeah. We build a max heap first. Yeah. We know the elements in this max heap not necessarily sorted. Okay? Yeah. So now the question, we want to make it sorted. How do we make it sorted? Yeah. Here. Yeah. First, we notice the largest element is at the root. Root element must be the largest. Okay, so that's the first simple observation. Yeah. After that, then our next question. In order to make the whole array sorted, basically, we make all the elements in place, right? Yeah. So what we are going to do, make all the elements in place. All right, yeah. When we make the elements in place, we do it one by one. Every time we just make one element in place. How about that? So one by one way. One way. All right, so now we know the largest element is at the root. Can we make the largest element in place first? It's very easy, right? All right, yeah. All right, so now let's make the largest element in place. Yeah. How to put it in place? Yeah. So let's imagine the array is arranged in this natural arrangement. Yeah. We know the largest element is supposed to be at the end, right? But currently it is at root. It is at the location 1, right? Currently it is at the location 1. Yeah. So that's the current location. Okay? Yeah. 1. Index 1. Yeah. But it is final position should be at the end, the last one. Yeah. Current at 1, but the in place location, the last one. How do we make that change? Very simple. A swap operation. How about that? Swap the root and the last element in the array. One swap operation. We put one element in place. Okay? Yeah. So we just do this. Swap A of 1 and A of n. One operation, okay? Put one element in place. But after that, because after you do the swap, the last element, you place it at the root, you violate max heap property, right? After we violate the max heap property, how do we fix it? How do we fix it? Right? Yeah. Because in the whole heap, only the element at the root causes the violation. Violation occurs at only one place. So we can fix it, using the max heapify, that operation, we fix it, reach the bottom. Yeah. But when we get to the bottom, we eliminate this already in place element in the heap. In the new heap, do not count this. New heap, do not count the, let me say this, count the in place elements. Those already in place, why you need to touch them, right? Because every time you put one in place, and more and more elements in place, after you put them in place, never touch them anymore, right? Never touch, do not bother them, right? Yeah. So you reduce the heap size, right? Every time you eliminate one element from the heap, so you reduce the heap size. Eventually, you put all elements in place, the max heap is gone, right? The max heap is gone, and the whole array gets sorted. Yeah. All right. So recover the heap structure, so using the max heapify operation. Yeah. So we keep doing this again and again until we get all the elements in place. So that's the heap sort. That's the heap sort. Okay? All right. Yeah. Next, based on the heap sort procedure, we want to see the efficiency. Okay? Yeah. Efficiency. Overall cost to do the heap sort. Yeah. All right. Here, so look at the pseudocode for that procedure. Yeah. It's pretty simple. Yeah. Build a max heap first. Right? Suppose we have that operation. Build max heap. Yeah. After that, then we do heap sort. Yeah. I equals n. Yeah. I start from n. Yeah. So location from 1 through n. All the elements in this range belong to the original max heap. Yeah. After that, we reduce the heap size. Finally reduce the heap size n to 2, and so on. Yeah. Because the last element 1 do nothing, right? When your the last heap has 2 elements, then you need to do one swap, one final operation. If your heap only has 1 element, it is already in place. So do nothing. So that's why we make the last I to be 2, not 1. Yeah. All right. Swap A of 1 and A of I. Every time I reduce by 1, so you swap that A of 1 at the root with the element at the last element of the heap, of the max heap. excluding all the elements in place. Okay. Then after that, you reduce the heap size by 1. But you need to fix max heapify, apply max heapify on the heap, starting at the root node with position index number 1. Yeah. Then after you complete the whole for loop, all the iterations, you get the array sorted. So that's the implementation pseudocode. Yeah. All right. Then the efficiency part, very straightforward. Yeah. So we can see it easily. Yeah. This is our max heap. Yeah. All right. Then look at the first time we do one swap operation, right? Then do max heapify. What is the cost? Max heapify. All right. Yeah. Log of n. Log of n. Yeah. The next time the heap size reduced by 1, yeah. Actually, probably you can argue. Yeah, you can argue it is log of n minus 1. Yeah, because the last element already in place, you exclude it, right? Yeah, it's okay. Precisely, it is log of n minus 1. Okay, precisely, yeah. So the next time you reduce the heap size by 1, so log of n minus 2, and so on. The last one, log of 2. Yeah. And these numbers less than or equal to approximately n log n. How about that? N log n. Okay? Yeah, n log n. Yeah. N log n. Yeah. Here we do a very rough estimate. Actually, we can do much more precise, accurate, rigorous estimate than this one. Yeah, but the result the same, so it's not necessary to go to do that much work because we can use the integral. Integral method to do the estimate of that summation with much better estimate. Much more much tighter estimate. Yeah. But the result still some multiple times that, yeah, actually the result still n log n, but minus, so some n something, okay, minus n something. Yeah. So the improvement is this minus n. Yeah. The dominant term still that one. Yeah. So for that reason, we just get this directly, right? Get that directly. Yeah. All right. If you want to do practice, then you can do that. Yeah. Here for my side, I just skip it. Okay. I just skip it. Yeah. All right. So we complete the whole heap sort and analysis. Yeah. So everything. Yeah. Then next, I still have some time, so I like to talk about idea related to a practice project. Yeah. Some interesting practice project I like to talk about a little bit. Yeah, because in this part we talk about dynamic data, right? Dynamic data. So I like to create a project as a practice project. You do not need to turn in because the semester will end soon, so you do not have chance to do it. But just if you like to do a practice by yourself, you can do as a practice project. Okay, yeah. All right, so let me stop this video here.